Okay, hi everyone, good afternoon. I am Devraj Das. I'm one of the co-founders of Hortonworks, and I have been in the space of Hadoop for more time than I would like to admit. And I presently manage and lead the HBase and Phoenix efforts at Hortonworks. I'm sharing the stage with Sudarshan Kadambi. He is an architect at Bloomberg, and today we'll be covering the high availability aspects in HBase. Okay. So to set the stage for the talk, let me cover some HBase basics. So the data in HBase are sharded by regions, are sharded by the regions, right? And the regions are hosted in region servers. Every region has a mem store, okay? And when a client sends an edit, the data ends up in the mem store and in something called as the write-ahead log. Okay? And when the mem store becomes full, it is flushed, and it becomes an H file and stored in the HDFS. Okay? So the data that you're talking about is the write-ahead log, which stores the in-progress writes, and whatever has been persisted is in the H file. Okay? So the data is all in the HDFS, and should the region server die, we could recover the in-progress writes by looking at the write-ahead log. Okay? So this gives a somewhat complete picture of the components involved in providing the HBase service. One of the most critical components in HBase is the Zookeeper. Okay? So when region servers come up, they register themselves with Zookeeper. And when they die, the master would get notified. Okay? And once the master gets notified, the master would reassign the regions that were on that server to other region servers that are available in the cluster at that point of time. Okay? And then the master would trigger the log recovery, the wall recovery process. Okay? And prior to the work that happened in the HBase MTTR, we would see roughly 3 minutes of downtime when a server goes down for the regions that were resident on that server. And the HBase dev community, the development community, did a lot of work and actually brought down the downtime from 3 minutes to less than a minute. Okay? The improvements were in the reduction of I/O that happens during the recovery process. Picking the right nodes to participate in the recovery process, et cetera, really helped. Okay? So, and notice this, that when the recovery is happening, the client is still waiting anxiously for his data, right? He has sent the request, and maybe he's just retrying to get the data, and the master is doing the recovery process. So we would like to actually reduce the downtime to a minimum, right? So that's the whole idea of the recovery process. Okay, so by tuning all the timeouts in Zookeeper, for example, we could get the MTTR down to 30 seconds, okay? But we could not go much lesser than that, because we would then risk introducing a lot of false positives, right? We would detect failures, which are actually not failures. They are just very transient network issues, for example, right? So we have to have a trade-off there. So 20 to 30 seconds is the worst case detection time that you're talking about, or best case, sorry, the detection time that you're talking about, right? And so, excuse my throat. What we have seen in the field, and Sudarshan is going to cover that in more detail, is that there are some applications that cannot tolerate these kinds of spikes in their latency responses, right? They want to have a much smoother latency response or latency curve. Okay. However, in HBase, as I said before, the data has to be recovered in a different region server, and only then it can be served out to clients, right? So it's because it's strictly consistent, right? So we then introduced in HBase the notions of relaxed consistency, okay? Certain applications can tolerate relaxed consistency in favor of availability. So that was the motivation for the work that we did that I'm going to talk about now. And it's for reads. We haven't covered writes in this work. So we introduced the concept of region replica in HBase and timeline consistency in HBase. And all that is captured in the Apache Jira HBase 170. All right, so what is region replica? It's a very simple concept. when you define a table, you can say, I want so many replicas for the regions of my table, right? So you can say replication count equal to 3, for example. So every region for the table will have 3 replicas, right? So what happens is that the master would create these replicas and would assign these replicas to region servers that are in different failure zones. So for example, if you have multiple racks in the cluster, the replicas would be assigned to different racks, so that even if one rack goes down, you still have the data in a different rack, right? Or replica in a different rack. It's very similar to the way HDFS does block placements. And out of the replicas, one replica is designated as the primary, and only that replica can accept writes. Okay? And all the other replicas actually are just following the primary, okay, by way of something called as asynchronous wall replication. Okay, so replication is in general a well-known tool in HBase that basically is used for inter-data center replication, right? You want to have the edits in a different cluster just for the sake of disaster recovery, right? So the edits are shipped from this cluster to a different cluster, and they're applied in a different cluster. So we have this inter-data center replication as a well-known topic in HBase, a well-known concept in HBase. What we did as part of the work was to make that pluggable, the whole replication mechanism. Okay, so we introduced the intra-cluster replication also as part of this work. So the edits could be replicated within a cluster, right, as part of this work. So the secondaries that we have there are basically getting the edits, right, from the primary, and they are applying the edits in their memory. No, they don't have walls, right? It's only in their memory, okay? So they share the same data files as the primary has. Okay, so the primary would flush the mem stores, and the secondaries would just read the data that was flushed. And the most recent updates are in the memory of the secondaries. Okay, so because they use replication, the secondaries may not have seen the latest data. They may be lagging behind a little bit. Okay, so this is an example of how things work. So let's say a client comes along and so for this region, we have 3 replicas. And a client comes along and he sends a write. So the write goes to the primary, and it's in the mem store, as you can see there, x equal to 1. And the primary also wrote that data in the write-ahead log. It would get replicated to the other replicas. And sure enough, the replication happened. So it's there in the mem stores of all the other replicas. And let's say a client comes along to read the value of x. Right. So here, what would happen is that the client's the RPC that is sent to the primary first. Okay, and only if there is a timeout on the primary would the RPC go to the other replicas. Okay, and whoever responds first is the winner on the client side. Okay, so the client would treat that response as the the successful response and move ahead. Okay. So here's another example. So the client is writing x equal to 2 this time, right? So it went to the primary, it got recorded in the mem store and in the write-ahead log. And then a client came along, and let's say for whatever reason, the replication couldn't happen to the third replica. And if the third replica happened to be the fastest in terms of the response, the client would see stale data, right? The client would see the earlier value of x as opposed to the latest value, right? So this is what can happen in this model, okay? And we had used APIs that you can use to explicitly control the consistency. So there is something called as timeline consistency here that you can set for your gets or the scan APIs in HBase. And when you get back the result, you can actually inspect the result to see whether it is stale or not, okay? And based on that, you can either discard the result if you wanted to, or treat the result as good and move ahead. Okay. So the default consistency is still the strong consistency, and this is this is something that you can use for applications if they don't care about consistency that much. I think that's pretty much from my side at this point, and I will now hand over the stage to Sudarshan.
Thanks, Devraj. Hi, folks. Standby replicas and timeline consistency has been made available in HBase 1.1. This feature is well suited for applications such as Bloomberg's price history, where read availability is paramount, but write availability isn't so. Loss of write availability is less catastrophic, as ingestion into the data store is largely through a batch pipeline that is run after close of financial markets. 170 does have its limitations, such as the potential loss of consistency while performing HA reads. While we were looking at the solution space more than a year ago, 170 was the quickest and the simplest to implement. In the time since we first looked at this problem, other solutions have come to the fore, and we are happy to note that this is an area of fervent activity within the HBase community today. First, let's look at some of the extensions to 170 beyond what already shipped in 1.1. A first possible extension is standby-aware assignment managers. When a region server goes down, the regions get reassigned by the master. Now, any region server could be chosen as the new home for a given region. It is advantageous to choose the region servers that were already hosting the standby replicas and promote those to be the primary. This exploits the warm block cache of the standby replicas, populated by the reads that failed over during the lifetime of the primary. This helps achieve good post-recovery read performance. A second extension is standby-aware data node placement. This leverages a well-known HDFS feature called favored nodes in order to provide hints to HDFS to place the secondary and tertiary copy of the data at the standby replicas. This has the advantage that for reads that fail over, for blocks that are not already in cache, the reads will still be local to the node and can still be short-circuited to bypass the data node. A third extension is pluggable retry policies. In our solution, the client issues a read request to the primary each and every time. Only if the primary is unavailable is the request reissued to the standby replicas. Instead, we could build a retry policy that keeps state about these failover reads and blacklist the primary if the number of failover reads exceeds some threshold in a given unit of time, after which we bypass the primary and go directly to the standbys. A fourth and final extension is pluggable consistency models. As part of the 170 work, we introduced the notion of replicas into many of the foundational HBase classes. We could extend it to provide quorum consistency with the ability to set read or write quorum at either table creation or at query time. As I mentioned, there has been a fair bit of discussion recently about alternate mechanisms of HA within the HBase community. Let's first examine what are the degrees of freedom available in the solution. We first need to decide what happens to the write-ahead log. Does the wall remain on HDFS, or does it get persisted on the local file system? If there are going to be multiple region servers participating in the write quorum and managing the wall independently, the wall should not remain on HDFS, because A, that would create more copies than necessary, and B, we would slow down writes drastically through this dual replication at the HBase and HDFS level. Second, our region server is going to be active-active or active standby in our solution. By active-active, we mean the client can issue a read or a write request to any replica at random in the replica set for a given region. By active standby, we mean there is an explicit notion of a leader replica, and a client issues a request to the standby only if the leader is unavailable. Third, do region servers attempt to seek consensus among themselves before persisting a write request in the mem store and the wall? Fourth, what sort of consensus algorithm should we use to try and achieve quorum? Some of the well-known consensus algorithms are ZAB, Paxos, and Draft. Paxos has historically dominated the academic discussion around consensus algorithms. But it is somewhat inaccessible. It is notoriously difficult to understand despite numerous attempts at explaining it in a simple way. The Paxos specification is also incomplete as far as some practical aspects of system implementation go. How we do leader election, log replication, or even address timeouts is largely left as an exercise to the system designer. A newer consensus protocol to emerge out of Stanford in 2013-2014 is Raft. Raft is roughly equivalent to multi-Paxos, It was designed with the explicit goal of being simple to understand. Raft has numerous open source implementations in a variety of programming languages owing to this simplicity. Raft's simplicity is due to its explicit notions of leadership, whereas in Paxos, every node in the quorum are true peers, and any participant can propose a consensus vote. In a minute, we'll see what is the effect of these different consensus algorithms on the eventual HA solution. Let's now look at some of the alternate HA mechanisms that are currently in development. The specifics of the system aren't so important. What we want to do is to be able to extract some architectural patterns that are reusable for high availability. We'll first look at WANDisco's nonstop HBase. WANDisco is looking to ship a commercial distribution of HBase explicitly built from ground up for high availability reads and writes. Let's now try and answer some of the questions that we raised before. In the WANDisco architecture, the wall is not on HDFS, it's persisted on the local file system. Multiple region servers have ownership of a given region and manage the wall for it independently. There is no explicit notion of leaders and followers. Any replica in the replica set of a region can be on the serve path for a read or a write request. The consensus algorithm is Paxos. On the write path, the client first looks up meta. There could be multiple copies of meta as well. It identifies all the replicas in the replica set and chooses one at random and sends it the write request. The chosen replica initiates the Paxos coordination with its peers. It ensures that quorum is established before the write is persisted in the mem store and in the wall. Let's try and understand this with a diagram. For a particular region, there are 3 replicas in the replica set, R1, R2, R3. The client picks a replica at random for issuing a write request, write x equal to 2. The replica that is chosen is R1. R1's responsibility is to now propagate the updates to the other replicas in the replica set. At the moment that the write consensus was in progress, there was a network partition. R1 failed to propagate the update to R3. So the write is persisted on R1 and on R2. Since majority quorum in a replica factor of 3 is 2, success is returned back to the client. On the read path, the client again picks a replica at random and issues the read request to it. Now, the chosen replica could be unavailable, upon which the client will perform an implicit coordinated read, send out the request to all the other replicas in the replica set, and use the answer from whoever responded first. So let's see how this works. The client again chose R1 to issue the read request, but R1 was unavailable. So upon a timeout, the client reissues the RPC calls to R2 and R3. Now, either one of them could respond back to the client. Remember that in a prior write consensus for the value x equal to 2, R3 did not participate due to a network partition. So R2 has the value x equal to 2, R3 does not. If R2 happened to be the one to respond first to the client will get up-to-date data. If R3 responded first to the client will see stale data. So the read semantics in this solution is the same as what we've implemented for 170, which is timeline consistency. Updates are always seen in order, but you could be behind in time. In summary, there is no downtime for reads and writes upon a region server failure. A region server that is unavailable might still be on the critical path for a write and will not persist the write. A region server that is unavailable might be on the critical path for a read, but upon a timeout, the client will reissue the request to other replicas. So let's pick another solution to compare this with. Facebook has developed a system called HydraBase based on their internal fork of HBase. Facebook Messages is a well-known application of HBase. When a region server becomes unavailable, a user loses access to his mailbox if that mailbox was hosted on the region server that went down. Facebook could set up multiple clusters with multi-master async replication between them and failover reads and writes to another cluster when a region server in the original cluster went down. The issue is, due to the asynchronous propagation of updates, failover reads will not be strongly consistent, and this could be toxic to some applications. There is a need for a cluster to be able to span multiple availability zones without any loss of consistency. HydraBase seeks to provide that. As with the WANDisco solution, the wall is no longer on HDFS, it's persisted on the local file system. Again, multiple region servers have ownership of a given region and manage the wall for it independently. In contrast, there is exactly a single replica that is designated the leader replica. The client issues read and write requests only to the leader replica. This directly follows from the consensus algorithm that's used internally, which is Raft. Furthermore, replicas are in either active mode or witness mode. An active replica does data management. It maintains the memstore, it maintains the write-ahead log. When the memstore fills up, it flushes it as a H file onto HDFS. It does periodic compactions. In other words, it behaves as a region server does in HBase today. Witness replicas only do wall replication. It maintains the memstore, it maintains the write-ahead log. When the memstore fills up, it simply discards the contents of the memstore. So let's see this in action with a few diagrams. Here, we see a HydraBase deployment across 3 availability zones, D1, D2, and D3. These availability zones could be multiple clusters in multiple data centers or multiple clusters in the same data center. There is a single replica, RS1 and D1, that is designated the active leader. There is a single replica that's active leader across all of the availability zones. Within each availability zone, there is exactly one replica that is designated active. All the other replicas are designated witness. So RS1 is active in D1, RS2 is active in D2. There are no active replicas in D3. There are 3 copies of data in HDFS in D1, 3 copies of data in HDFS in D2 that is managed by RS1 and RS2 correspondingly. There is a 5th witness replica, RS1 in D3, that is run so that majority quorum can be established even if an entire data center went down. We will see more about this in a minute. The client issues read and write requests only to the active leader, in this instance, RS1 in D1. When the client issues a write request, it's the responsibility of the active leader to use the Raft consensus protocol to ensure that a majority of the replicas in other availability zones have persisted the write. In this case, it would be 3. When the active leader goes down, a new leader gets elected. In this case, it happens to be the replica RS2 in the same cluster. If the entire data center went down or the entire availability zone went down, a new leader is elected. In this instance, it happens to be RS2 in D2. The client will now issue read and write requests to it. So what is the implication of having an explicit leader? The window of downtime in the HydraBase solution is more than it is for both WANDisco and 170. Why is it so? If you have an explicit leader, and if the leader becomes unavailable, we need to detect that the leader is unavailable. It's a distributed system. The only way to detect failures is through timeouts. And B, we need to perform a leader election to generate a new leader. These operations typically take tens of seconds. This is the price to pay for strong consistency in the solution. So now that we have a fair bit of understanding about both the WANDisco, the HydraBase solution, as well as 170, let's try and put it all together. There is a very important HA mechanism that we haven't already covered. Replicating to another cluster is a valid way of achieving high availability. This is a feature that's been available in HBase for over 5 years now. For those of you who don't know, HBase's native replication is asynchronous and is not consensus-based. Reads and writes can be highly available, but there is a latency penalty for forwarding read and write requests to a different availability zone in a different data center. Reads and writes are not strongly consistent. But if I set up multi-master async replication, the write could get applied in any cluster and will become globally available eventually. Interestingly, 170 can be combined with HBase's native async replication for asynchronous propagation of updates both within and between clusters. Let's now look at some of these properties in the comparison matrix to see how these solutions face off. First is the consensus algorithm. Intercluster replication and HBase 170 do not use any consensus algorithms. WANDisco ships with a commercial implementation of their Paxos engine. HydraBase designers went with their own implementation of the Raft protocol, but as I mentioned before, there are plenty of open source implementations available out there. All of these solutions help improve read availability, and that's a plus. The only solution that does not come with native write availability improvements is 170, but this can be combined with intercluster replication, and we can asynchronously propagate updates to a different cluster, failover writes to a different cluster. The only solution that does help improve strong consistency semantics of HA reads is HydraBase. As we've discussed before, there is a price to pay here. The window of downtime for electing a new leader could be significant and could be tens of seconds. Both WANDisco and HydraBase, due to the nature of quorum writes, do support strongly consistent HA writes. HBase 170 by itself is not designed in a multi-data center configuration, but could be combined with intercluster replication to work across data centers. None of the solutions support true pluggable consistency models. Even though two of the solutions, WANDisco and HydraBase, do support quorum consistency, since they don't allow explicit setting of the read and the write quorum size, the effort to extend any one of these solutions to achieve true per query consistency tuning is likely to be significant. So enough theory. If you have a HBase deployment and are looking to see what are the HA options available for you, what do you have in front of you? Intercluster replication and HBase 170 are both part of mainline HBase. Intercluster replication has been part of HBase for the last 5 years, production ready, battle tested. HBase 170 has been part of HBase 1.1, a release candidate for which was shipped out about 2 weeks ago. This has been deployed on the Bloomberg clusters. WANDisco is looking to ship a commercial distribution of HBase that is API compatible with HBase 0.98 and upwards. HydraBase today exists as a proprietary implementation inside of Facebook. There are some JIRAs open for the initial open sourcing of it, but the effort to integrate something like HydraBase into mainline HBase is likely to be quite significant. In summary, HBase lacks a true quorum consistency option today, and this is sorely needed. Given the effort it will take to implement something like this and the duration of implementation, it's good for us to start putting it on our radars today. We are happy to note the multiple efforts at solving HA within HBase. We are hoping that all of them will converge towards a single solution. We'd like to thank a couple of people, Jagain Sundar and Ryan Rossen from the WANDisco team, and the HBase team at Facebook for their valuable inputs. Thank you. We have more than 10 minutes now. We'd be happy to take questions.
I saw that some solutions, they have read inconsistency. So I'm just wondering if client wants to do a further update and it is working off stale data, it can cause real problem. So for example, original value of X was 1, somebody updated to 2, and now a client is trying to change, like, okay, increase the value by 1. So if it read the old value of 1, it will set the new value to 2, whereas the new value should have been 3.
That's right. Let me go with a specific example. In the price history application, we have two kinds of reads. One is Readmodifywrite, wherein, let's say time series data is stored in month blobs. So an entire month of data is encoded in a single cell in HBase. If I get pricing information for a new day, we have to read the entire month blob, modify the data for today, and then write it back. When you're performing read for the purpose of writes, you don't want to enable timeline consistency, because that will introduce stale data into your database, and then it'll be very hard to detect such problems. But when you want to serve up the read to a client, it may be acceptable for the data to be stale, because you have a batch ingestion pipeline that's producing newer pricing data. Even if you're behind by 5 minutes in serving up a read request, that is acceptable. So we make a distinction of what is the purpose of the read. Are we going to be taking this value, modifying it, and writing it back to the database? Hence, in that instance, we will not do timeline consistent reads. But if you're just going to be serving it up to the client, we will, because high availability becomes important there.
Okay. Thank you.
Question? You said for the reader takeover of the HydraBase will take tens of seconds. So is that a number Facebook reported, or is that something in general?
No. The detection time is the same as detection time in HBase, right? You don't want to make the detection time too low, because that would cause data churn. You don't want to switch the leader replica back and forth between data centers. There is some cost to doing that. So detection times are typically tens of seconds, accounting for temporary network blips and Java GC, et cetera.
So majority of the time is a detection for timeout part.
That's right.
I see. Thank you.
Hi. The comparison matrix seems to leave out the cluster utilization part for solutions. If I look at the Facebook solution, it seems to only use like 1/3 of the cluster for client requests, but everything else uses like as much as possible all the servers. Is that true? Like only 33% of the cluster will get used in Facebook solution.
That is the view for a single region, right? So there are 5 replicas for a single region, but a different region server could be the leader replica for a different region. So in aggregate, the requests will be well balanced across the cluster.
So there are no two different sets of servers. They are the same servers, some hosting primary, some hosting witness.
I see. Could you use the mic, please? So
I'd like to know what's the HBase direction in the future to achieve the same as HydraBase HA.
Those solutions need to be integrated into mainline HBase. Nobody wants to run a fork of HBase. Some enterprises might be willing to buy a commercial product, and Vandisco does ship a commercial product. But for those of us who are looking for a pure open source implementation, we are looking to take some of the architectural patterns available elsewhere, reuse them, and apply them to mainline HBase.
So do you have any prediction, in which version probably will?
I can't predict the specific version, but some of us are looking into it actively. Towards the end of next year, we hope to have the basics of something.
Okay, thanks.
Okay, that's it. All right. Thank you.
Thanks, guys.